Let's take another look at how we set up freefall problems and represent their motion. In this problem here, we have Emmy down at the ground level, and she tosses a ball. It travels upwards, it goes past Albert, higher above him, and then comes back down and lands in his hand. So our first step is the sketch showing the events. In any problem, we could put all sorts of different events. The key to choosing good events is simply to ask the question, at what moments in time do we know things about the problem, and what moments in time are we interested in finding out things? So we've been given information about the starting point here, and we're interested in when Albert catches the ball up here. And so that helps us to make our decision. We have one event down here. And when we describe freefall events, words like these are really important. We don't want to say something like Emmy throws the ball. Throwing a ball is an interval of time. And we saw something similar to that in our previous work here. Throwing the ball is an interval of time where the ball is speeding up. Here we want to be very careful. This is when the ball leaves contact with Emmy's hand. So it's not the throwing the ball interval. And over here, this is when the ball contacts Albert's hand. If we say something like he catches it or he stops the ball, that might be describing the interval of time while the ball is in contact with his hand and is slowing down. So we want to be super careful here. An important part of our understanding here is that event 2, the ball is still moving quickly. It has only just contacted Albert's hand, and that's what ends the free fall interval. Just like this is what begins the free fall interval. We need to be super careful that we don't include intervals of time while there are other interactions with the ball. While Emmy is pushing on the ball in order to throw it, or while Albert is pushing on the ball in order to catch it and slow it down. So we have to be super careful. With our choice of events here, between event 1 and event 2, the only interaction is the gravitational interaction. And so this is the interval of free fall that we are looking for. Let's write down our givens. So the ball leaves Emmy's hand with a velocity of 12 meters per second. So that'll be v1. And Albert catches the ball 6 meters above Emmy's hand. So if we choose this as the vertical origin, then at this position here, with a displacement of 6 meters in the upwards direction, Albert is catching the ball. Now, here's an important piece of our understanding about how vectors work and also how the big five equations work. It doesn't matter how far this ball travels above Albert before he catches it. What this is telling us is that the ball is at a vertical position of 6 meters above its start at event 2. So it could have traveled much, much higher before Albert catches it. But at the moment he catches it, it is 6 meters above its starting point here. And so that's why displacement is such a powerful idea compared with describing the distance the ball might be traveling. A lot of people wonder, do we need to put an event at this point here, the highest point in the trip? And the way that we decide that is by asking the question, are we interested in finding out anything about the ball at this moment in time? And the answer is no. We could ask a different question, how high does the ball go above Emmy? But we're simply not interested in that. Because this interval here is free fall and has constant acceleration during this whole time, the acceleration does not change, we can use a single big five equation to describe this interval of motion. This is why the big five is so powerful. Even if an object turns around, if the velocity changes direction, we can still use the big five as long as the acceleration is constant for the entire interval. Now, between this interval of time, the ball is accelerating. It has its free fall acceleration. We've called upwards the positive y direction, and so the free fall acceleration is going to be downwards in the negative y direction, negative 9.8 meters per second squared. Our goal is to find the time that it takes. So our givens and unknowns, good. Conversions, our units are all meters and seconds, so no conversions are required. Let's take a look at how we represent this motion using our motion diagram and graphs. At event 1, the ball is at the origin, and it leaves contact with Emmy's hand. At this moment in time, it's moving quickly. So there's event 1, and because it's moving quickly, it starts off with large spaces between the dots. Because the acceleration is in the negative direction and its velocity is in the positive direction, the ball is slowing down. And so the spacing between the dots is going to get smaller. Whenever you draw your motion diagrams with acceleration, make sure each interval is clearly smaller. It reaches its highest point up here, and then it turns around and comes back down for a short distance. So I'm going to show that over on this side here. And let's say it's right there when Albert catches it. So for this interval here, we can see the spacing of the dots is getting larger. That means it is speeding up. Let's think about the position graph. At event 1, the ball is at the vertical origin, so we're going to show that here. At event 2, the ball is higher up. It's above the vertical origin. Between these two events, the ball travels to a higher position and then back down to a slightly lower position. So how do we connect these two event points? Since this is a position graph and it is accelerated motion, its velocity is always changing. And that means its slope has to always be changing. So this must be a curve. So it's going to travel upwards past Albert, turn around, and come back down to Albert. Remember, we're simply not interested at this moment in time when it reaches its highest point. There's no event number there. Okay, let's take a look at the velocity graph. Whenever we have two graphs that are drawn one above the other, take extra care to line up the features of the graph in time. So at event 1, the ball is moving quickly in the positive direction. So we'll show a large positive value there. At event 2, it's going to be moving in the negative direction. Now, it won't be as fast as this speed over here. So at event 2, we're going to show it with a smaller but negative velocity value. It's moving downwards now. And now how do we connect these dots? This is a velocity graph. During this interval from 1 to 2, the acceleration is constant. So this must be a straight line between these 2 points. Now, what's helpful for us to notice here is that at this moment in time, the velocity value is equal to 0. And so that's going to match up with this moment here in the position graph when it reaches its highest point. The slope of the tangent to the position graph right at this moment is 0. It's a horizontal tangent. And that corresponds to this velocity of 0. Now, a helpful word about language. At this moment in time, we will never say that the ball is at rest. When we say the phrase at rest, that gives you the picture of an object whose velocity is 0 for an interval of time, like it's just sitting there. But this is an instantaneous velocity of 0. So it's just one moment in time when the velocity value is 0. Just before and after, it's moving. So just be really careful. When the velocity is 0, just for one moment in time, we never use the phrase at rest. Now for the velocity vectors. At event 1, it's moving quickly in the positive direction. So velocity 1 vector. And at event 2, it's moving in the negative direction, but not quite as fast. So important pieces of our understanding of free fall motion. During this interval of time, the only interaction with the object is the gravitational interaction with the Earth. So that's why it's free fall. And so this interval of free fall describes upwards motion and downwards motion. And we can treat this as one interval of time for the purpose of our math work, because between events 1 and 2, the acceleration is constant. There's no difference between the acceleration during this interval and this interval. The slope of the velocity graph is the same here as it is here. It's negative, acceleration value, negative 9.8 meters per second squared.